Okay, good morning, students. Where we last left off was touching on the ideal vapor compression cycle, right? And this should have looked familiar to you. And like I said, the section is not particularly difficult. And yeah, if you follow through the textbook and its examples, you should be more than ready for the section. Students do fairly well on this particular section. In fact, the next three sections of thermals are not that difficult actually, and possibly the fourth one if we actually do get there. But typically I normally cover 6. But yeah, I think by next semester, or well, next time I do this, I'll probably have extra 2 sections. Yeah, but then again, obviously one can't go to a lot of detail. So we are basically left off. I'll probably just have this graph over here. Is just a quick slight recap. So our refrigeration cycle is a thermodynamic cycle. It's made up of 4 processes, and one would be an isentropic compression. That's through a compressor. We've got a rejection during a condenser. Obviously, there's throttle, which is an isentropic process. I have it over here. We assume that the entropy remains constant. And then furthermore, we have a constant pressure heat addition through the evaporator. We can normally start at 0.4 to 1 and 1 to 2, 2 to 3, and so forth. And yeah, we've also learned something called the COP, and the COP is the efficiency metric for refrigeration cycles. And we found that it's greater than 1. So it's a very efficient device in terms of energy conversion. So we get more on what we put in, right? Arguably, obviously, we did our basic analysis on that. So what I decided to do, what I wanted to touch on here, there was something I wanted to actually bring out, more of an investigation type problem, and that was to really look at the effects of the condensing pressure and the effects of the evaporating pressure as well. I wanted to do like an investigation over here, and I decided, okay, I'm not going to actually just do that and just actually start on an actual cycle. We can solve a few problems, but I wanted to do, because I have a bit of experience with this kind of particular process. This analysis kind of stuff, like practical, and I thought I'd make it interesting, but obviously in the interest of time, we don't want to really unpack that kind of stuff. So we rather just get to what we need to do. Okay, so we're going from the ideal, and now we're going to start on the actual vapor compression cycle. All right, so it nearly looks the same, and the analysis is fairly the same. However, there are a few things which changes, right? Let me just quickly see. So I'm saying the actual vapor compression cycle is different from the standard one due to the following reasons. One is that liquid refrigerant condenser subcooled to ensure 100% liquid entering expansion valve. I'll talk to that. So what it means is that we assume after it goes to the condenser, which is essentially from 0.2 to 4 here, right? It's not particularly more complicated. Okay, so yeah, anyway, so we assume that when we're condensing, we actually we are hoping that the gas is basically 100% liquid. However, in practical circumstances, this doesn't always happen. So what happens is we subcool the liquid basically before it enters the expansion valve to make sure that it's solely liquid. So that's the first thing we do. The second thing we also do is on the compressor side. So if you look at the evaporator side, which is essentially from 6 to 1 or 8, don't worry about all those numbers, you won't be finding all those points. And we assume that the same with the evaporation side. So when it evaporates, we assume that it's going to be perfectly a vapor or gas, so to say. However, that's not the case, and obviously we don't want a liquid to enter the compressor or damage the compressor. In fact, liquids or I guess categorized as incompressible, like we can't really compress like gases. So we make sure we superheat it, right? And all these processes are really controlled with the thermal expansion valve and things like that. But of course, like I said, we're not going to be focusing too much on the practical aspect of the refrigeration cycle, just more the thermodynamics, like as obviously as before with all the other stuff. Furthermore, we assume isentropic expansion and compression, but obviously this is not typically the case, right? There's also friction and other losses within the pipes, things like that. We also have pressure drops, obviously due to friction along the length of the pipe. So we won't particularly include all of the stuff in the analysis, but once you start doing the actual problems at the textbook, you'll see the different types of variations or what I might ask you. And I'm hoping I can touch on at least 3 or 4 of them before we start on heat transfer, because we will be starting on heat transfer in the next section. So I want to make you also aware with this particular section of refrigeration, it does go on to cascade systems. We have 2, and we also have 2 evaporators you could have. And furthermore, okay, this was just showing the software, and you can also have gas refrigeration over here. So there were other things which I want to touch on. There's obviously a bit of theory as well, and you know, like, and this happened last year as well, and I decided, no, I can't include all these things. It won't be fair on you guys. It's the amount of studying. It's just kind of ridiculous with the time frame. Obviously, so that has to be kind of worked out. So I'm cognizant of all your workload. We also get gas refrigeration cycle, which essentially it's the reverse of the Brayton cycle, which is also quite fun to do. Actually, it's quite easy to do. So I'm making you aware of how far this goes in terms of refrigeration. It's a very, very big section. But obviously, we have to squeeze in a bit of heat transfer. We have to squeeze in a bit of air compressors, and potential engine performance testing. So I don't think there's adequate time within our time to cover all these sections. However, the vapor compression is the main one, and that's typically covered. Yeah. So again, just to recap, with the actual vapor compression cycle, we've got the main thing was going to change that. Normally, point 1 was lying on the saturation line, if you remember, right? Where's point 1? In this case, it's going to be shifted to that side, and it will be superheated now. Therefore, we both have superheat at entry and at exit of the compressor, both the suction and discharge. There's a lot of cool things I could have done with this thing, which the textbook doesn't really talk to. And like I said, I didn't really want to bring that. Furthermore, again, remember we talked about this at point 3 with the compression. It's not completely isentropic. Therefore, we have to incorporate an isentropic efficiency. In fact, they're asking us to find it isentropic efficiency of the first example. Typically, with these types of examples, they actually give it to you. Like the same as your Brayton cycle, and obviously you have to compute it. So there's a few points which you're going to have to touch on within this problem, and like I said, I have a few more for us to actually solve. And I have around 3 which I want us to all get acquainted with. Guys, you can absolutely not get marks in this section. You have to just know your tables, take properties from it. Yeah, it's just no excuse not to score marks, especially for the next test. The next test, this is definitely in heat transfer, and then obviously air compressors will be in the next test. So please make sure you understand this. It's very easy. There's no mathematical tricks again. Very procedural, and one must just have ability to interpret the data. Okay, so I'll give you a moment, just like 2 minutes to get your textbook. Maybe if you have it open next to you, and that's going to be on page 614, and we'll be looking at our first actual cycle. You might ask what to expect on the test level. If, depending on the nature of the test, you might get an ideal cycle, and there's probably a 30% probability, but more than likely you get an actual one. So make sure you understand the ideal one. I mean, it is a possibility. I might give it to you, who knows, depends on the nature of the test. But the actual one is obviously what you actually want to know, because that it models the gas to vapor compression cycle fairly accurately. Cool, copy. So like I did say, yeah, there's a lot of investigations we can do and look at how different variables affect each other, but it's in the interest of time, we don't want to spend too much time on that. So I think let's just do a first example, then we can actually just get questions out of that through that example. Okay, so I'm just putting it up. So you guys can just get your textbook ready as well. Yeah. And you guys are aware that there are solutions available for the textbook, eh? It's on the, you should have it. There's a solution manual. So you should actually just get it. Can you guys hear me still? All right. Okay. Students, any questions? Okay, yeah, thank you. And again, guys, you know, for all my students, I'm going to say again, guys, just watch the lectures, watch it twice, watch it once, twice, do the problems with me. Yeah, you should at least get 50%. You can absolutely not fail. The stuff is advanced just by virtue of it being the way it is. All right. Okay. So from an analysis standpoint, what we're just really looking, what you're always going to have to find is your COP, and we're going to be looking at QL and WC. So what QL is, right? I just want you to be aware of two things here. So maybe, and this is why I want to talk about this particular pressure and temperature. You're always going to find that your food, if this is -10, right? And this should probably talk with the refrigerant. You're probably going to find your food at 0 degrees, right? So that your food can actually give heat there. We can't find a situation where this is -10. Otherwise, heat won't be actually removed. Remember, we heat moves from a high temperature to a low temperature. I'm just using, you could have used 5 degrees here. Furthermore, on the condenser side, your condensing medium can't be more than your condensing temperature, right? So in fact, here we're sitting with 50 to 26. So obviously this could have been around maybe 30 degrees here, right? Because this 50 degrees, what happens is it's basically giving heat off or rejecting it to the air, and hence the air will be cool up to 30. So your condensing temperature must always be higher than your actual whatever side. Otherwise, you're going to get heat in. So the purpose is you're going to have heat out. So this must be hotter and this must be colder. So that's just very important practical perspectives to look at in terms of this. But we will touch on a few examples. So we're always looking for the coefficient of performance, which is basically an efficiency metric. And we're always going to look for QL and WC. So can someone just tell me where is QL in between? Between which points? I'm just being obviously deliberate. Yeah, 4 and 1. So we normally say your mass flow between H1 minus H4. And you might be asking why we're using enthalpy. Remember, these are concentration processes, and CPs are always tied with H's, and CVs are always tied with U's. Obviously, it's all in keeping with the same principle. Your compressor, where's your compressor in now? Where's your compressor between? Sorry, your compressor. Yeah, your compressor. You're working from your compressor. Two and 1. That's correct. So this is where you're always going to be. I'll just call it H2 minus H1. And I'll probably say H2A here. This was a particular reason why I'm going to say that, but it's fine. So these three, you're always gonna end up finding they're always gonna be around 6 marks like this, right? So this is where you're always gonna be working towards anyway. Most of the questions, you're always gonna end up particularly finding this kind of setup. Nevertheless, how do we start? So with an actual cycle, remember, normally an ideal cycle, we have to find a saturation at point 1. So we're always going to start at, what do we say, P1. Of course, we can go process 1 to 2. T1 is minus 10. That's 0.14. Right? And this is now superheated. So remember, superheated is always coupled with the pressure and the temperature, right? Okay, so obviously I'll spend time on this particular example. I'm gonna make sure you guys get it. So remember, this is an actual cycle. How do you know it's an actual cycle? It's an actual cycle. Oh, it's an actual cycle because you've got superheat on entry, right? That's how you're gonna know. If it is on the saturation line, it'll be an ideal cycle. So this is how you'd know. So what we require to do now is go find our enthalpy value at point 1, which is essentially H1. Okay, so go to your tables and go find what H1 is. So you need to go to your superheat tables, and that table is going to be, make sure you please do it, A13, somewhere along A13. I highly recommend you go and go find it yourself. It's no point in me doing it for you. Obviously, the next you're probably going to get more confident and you're able to maneuver around, but make sure you go find that value for me. So in the actual cycle, on entry superheat, if I throw a free question, is the reason why we superheat it so that we ensure that the compressor is completely compressing vapor only and not a bit of liquid. We don't want to compress liquid. That's not our business, right? But just be aware of that. Something's wrong. All right. So can we get the H1 value? 246.37. Is that correct? How much people said? Yeah. Okay, I'm happy with that. Okay, 246.37 kilojoules per kilogram. Right? No, man, why do you do this to me? Okay, that's fine. So again, obviously this gets compressed to a pressure of 0.8 to 50 degrees now. So we follow a similar process. Okay, guys, my laptop just froze. So make sure what you just do now, you go check the pressure at 0.8 and possibly at 50 degrees. So that's the next point. Just go have a look at that one and get your next enthalpy point. I'm just going to restart my laptop quickly. Okay, do you guys manage that? Where's my whiteboard? Do you guys get the second point? No one's saying anything there. Okay, so like I said, you want to find your next point. Quite easy. Where are we? Where are we? Towards 6 point. Let me have a look at it myself. You guys managed to get that, so I'll just quickly show you guys a just a small guess for the ones who possibly don't know. Guys, I'm making you where you can interpolate here. So we said it was what? At minus 50 degrees, right? Interpolation is possible. So don't ever think that it's not possible. So just getting the table out here. 0. What you're first looking for is this 0.8, and then you're checking for 50 degrees, and then boom, that is it. Obviously, this is your H column here. That's your entropy column. So you should get. In fact, that is your H2 actual, right? So I'm making you aware that that is H2 actual. So let's write a thing called H2, right? H2A, right? Because remember, we're required to find that that isentropic efficiency. So make sure you call that H2A, right? And then this was 286 point something, 0.71. Great, I'm missing Ngwenya, 71. So guys, this is H. I'm going to find H2S one time, obviously, so we can find the isentropic efficiency, but I'm making you aware. So if you remember your isentropic efficiency, or normally when you find H2 actual, it's H1 over H2 minus H2S minus H1 over that. That's our typical thing. It's exactly the same thing as on your turbines. So I want us to find H2S while we're at this process 1 to 2, which is the compression. So to find H2S, we have to find S1, right? I'm just doing that now. So let's just go back to our saturation tables, not the superheated ones, and then just go check what S1 was. So let's just do it now while we are here. 0. Guys, quick, 0.9724 kilojoules per kilogram Kelvin. And then obviously we know that S1 equals S2. Therefore, what you have to do is go to that pressure. I think this was done already, maybe in the previous example. I think the previous example, or not the previous example, obviously the one in the textbook. Then we can find H2S. Great, I'm happy that you can find so fast. H2S is 282, right? Oh, students, can we all, what is it, 284.2? Students, can we all find that? Let me not assume that you guys can do it. Easy section, guys. Easy, easy, easy. Are we all happy with finding H2S? Students, are there any questions? Can you find H2S? Are we all happy with it before we move on? Can you have some thumbs up if you're able to find it? Please let me know. Anyone? Mr. Abreu, can you find this? Mr. Matoso, guys are not speaking to me here. What is required now is for us to find our next point. So when we're looking at this over here, so what happens is we get a slight pressure drop through the condenser, and we end off with two things over here. What is this? The refrigerant drops to a pressure of 0.72 to 26 degrees. So obviously, we need to now find our enthalpy, right? And how do we find our enthalpy? Where's an idea? Where do we get that enthalpy? Okay, it's no idea. So guys, one thing I want to make you aware of, right? Um, so you don't get confused. Yeah, 26 degrees liquid, yes. The reason why so for H3, so we can say P3 if you want, and 72 MPa, and T3 is 26 degrees. When we find your your liquid temperature on the superheat on an actual cycle, what you need to be aware of that your liquid enthalpy is predominantly a function of temperature and not pressure. Okay, so be aware that liquid is predominantly the enthalpy of liquid is predominantly a function of temperature, right? So when you're doing this, you can kind of ignore the pressure. Then if you go to your saturation tab at 26 degrees, you can find H3. So let's get H3. At 26 degrees, it's on your liquid side here. So it should be HF if I'm correct. Yes, Silas, go for it. Silas, was it a mistake?
Yeah, yes.
Yes,
Yeah, I just wanted to confirm something with you. There's a
go for it.
the reason why you're saying we should ignore the pressure there is it because I'm looking at that TS diagram where you have where you got your H3 actually at point 3,
Mm.
but it's also the same as H4, I think. Yeah, is
Yeah,
it?
point 4.
Yeah.
Yes, that's correct. And the reason why is because we're throttling, we're not losing any enthalpy. It's approximately the same.
Okay.
So I'm making you aware. I'm just making you aware. Yeah, on the actual cycle, sometimes they trick you and give you the pressure and a because remember a pressure drop does occur within the condenser. Obviously, if you think about a condenser, you can imagine how big a condenser is in terms of the tubing, in terms of the length. I'm sorry. So so obviously what happens is that there's a drop in pressure. However, the if we want to find the entropy, you just have to look at the temperature solely, and we're going to unpack a bit of a few more of these things. So I'm just making you aware of that. Okay, so let's get H3 quickly. Let's see what we get. And H3 is approximately equal to, like the thermodynamic chapter on refrigeration. There's a lot of things one can really add here in terms of teaching, but yeah. So let's just get H3. So we have to go to your liquid table, your saturation table, and go with the liquid check 26 degrees. You should find it. 87.83, fantastic. Okay. And what you should write is always H3 is approximately equal to H4. It doesn't or equal to. You get a mark for that. Kilojoules per kilogram. Okay. So in terms of marks again, 1, 2, 3, 4, 5, 6, 7. Just for getting properties, right? So let's try to just sort this out. Let's work out. So once you've done that, basically, you essentially sorted out. I will make you aware of what we need to kind of other things you want to add. But they're saying, oh, and yeah, they're saying this regarding any heat transfer pressure drops to connecting line. So let's work out QL, the heat removal, right? So again, QL is the heat removal. This is where your objects are, and it's extracting heat. So QL, and we want WC and WC. So QL, they gave us our mass flow rate, fortunately. Sometimes you have to work that out, and hopefully you'll touch on that. And your mass flow rate is going to be 0.05. H1 was 246.37 and H4 is 87.983. Furthermore, we can work out our work in, and obviously in this case we are fortunate to get the actual value, because normally we have to find the isentropic value and then convert it into the actual value. So I'm making you aware of that. So H2A is going to be 286.71 minus H1 is 246.37. So let's quickly get those values, work it out yourself, and obviously, if you divide this two, you can get the the COP, sorry. So it's not difficult really, but the variations are going to come now, so that's going to be fun. Just have a go at that. Okay, so here's a good question. If they don't give the mass, will we just do it per kilogram? Yes, But predominantly these questions, they're always the mass flow, either you have to compute it, but you can obviously find the COP without using the mass. But yeah, normally the answers are normally in kilowatt. Yeah, I'm telling you right now. So normally in kilowatt. So you're gonna have to find the mass. Yeah, the mass flow rate rather. Are there any questions before we move on? Sorry, man. I mean, I didn't actually know my mic was muted. So, were you guys able to calculate the QL, Q working? Is there any questions with the cycle before we move on to all the other good stuff? Please, guys, any question, I really appreciate it. You know, maybe it was Friday. That's why your brains were all out. Okay, great. So I'm gonna throw in a bonus question here, and be very well aware it can come in. So I'm gonna throw it over here, right? 20. And the question is as follows: the quality of the refrigerant at the end of the throttling process, right? This question is a typical question which comes up. Hope you guys can see it um, um, over there. Okay, cool. Cannot edit this. Okay. Anyway, so let's just ignore that. I'll just move it over here. So I'll just say the quality of the refrigerant after throttling. Okay. So if you remember when you're doing your steam stuff, you have to find the dryness fraction of the stream. So it's something similar. So what we are looking here is for the quality of this particular refrigerant. And I have to see, remember, because over here, this is liquid, vapor, and this is the gas realm, right? And of course, this is the superheated gas, right? This is a G. So by looking at this, judging from here to this whole line, and obviously this is 0% to 100%, how much do you think, what's the approximate percent of this, of the vapor? Off the cuff, right? Just having a look at this graph. I'll just make it. What percent do you think it is? Very important question. Definitely going to come up somewhere. Anyone? Just throw a percent there. Any random percent. How can it be 99% if zero is on the liquid side? Check where 0.4 is. Maybe you guys didn't get the question. I'm talking about 0.4. Remember, it's the quality of the refrigerant after the throttling process. One. Guess no one has. No one's everyone's intuition is good. 8 to 10%. Yeah, that's a start. Okay. So anyway, yeah, that's some guesses. Guess no one is really. So how do we find it? We have to say H4 is going to be equal to HF plus X HFG at, this will be at the pressure of 0.15, right? So at 150 kilopascals is where we're going to get these properties. Obviously H4 Silas has got for us, which was 87.83. And what we need to do now, and I'll let you do it, is find HF at 150 kilopascals plus HFG, right? Remember, this is your enthalpy of evaporation. So then obviously our only unknown will be X. So maybe Miss Nguena can find HF and HFG for us at 150. So guys, be aware on how to find the quality of the refrigerant because the will pop up. And the will definitely arise. Okay. So quickly, can we just quickly get that? Let's see the quality of the refrigerant. How much of it actually has vaporized, or like what's the state of it after the throttling? Because remember, it's supposed to be liquid. Let's see. Was an acceptable answer. 27,81. Mr. Demanus has. Mr. Manus, can you just hit me with that enthalpy values? I'm just gonna go to my table now and see if you're right. Guys, please get this, man. I don't know if you guys are still. I said 150, right? So we just have to divide this value. So I think HF is 27.06 plus 31.18 divided by 2, which will give us a specific value. Let me just see. Yeah, 29, yep, beautiful. Guys, this is a whole extra X and 211.045, yeah. And if you solve this, again, this would be getting this property is 1 mark, getting that property is another mark, and getting this to is an extra 4 marks. Extra 2 marks. So it's extra. So I'm not sure what my X value is there, and Mr. Minus, the prof is what 27.81%. So what it means after throttling, right, it's the vapor comes in as only 27.81% is actual it's vapor. It's not completely gas yet. So obviously then furthermore, what happens through the evaporator, then this 27.81 obviously will become in the excess of 100%, which is essentially superheated. So that basically the compressor doesn't get any and be aware of that, I might ask these practical type questions, but I'm not opting for it. Okay. Are we all happy with this? Any questions, students? Okay, can we do one more? Maybe 2 more. Any questions, students? So there will be no new concept above and beyond this, which I'm not trying to introduce, thank you. But if you're able to do this is then great. Let me just quickly see. I'm copying our next example here. So guys, I'm gonna do our last example, and then I will start on heat transfer. Yeah, and I hope you are able to solve the remaining actual problems within like I said, this is has become it's a big section, can be made big, but obviously one has to decide on what is important over here. Okay, so over here, so I like this one, and the reason why this should be 0.5 meters cubed per minute. So you're not talking about, you might have to work out your mass flow rate. So let's sketch our TS diagram. So they're saying the refrigerator enters a compressor at 100 kPa at that. So we know here it's probably superheated, so 0.1 MPa at minus 20 degrees. And it goes up and leaves at 0.8 MPa, which is essentially this line over here, like that, and like that. So something like that, yeah. Okay. We have it enters a throttling valve at 0.5, so that means that's 0.5 MPa, and this is at 26 degrees, right? Obviously, we know that this temperature must be higher. This doesn't have a temperature yet. We also have an isentropic efficiency of 0.78. So that means we have to first find H2S and then HA. This is like a test level type example. And it says it leaves the evaporator at saturated vapor at minus. So maybe this is like point, I don't know, maybe 0.5 or something. This is going to be 0.1, 0.1, 0.2. So at minus 26 degrees. Yeah, and obviously gets superheated. So first thing is first here, right? I'm going to test you guys. Okay. Let's find the mass flow rate of the system. Can someone give me the formal definition of mass flow rate? No, man, like the formula mass per unit time is fine, yeah, but like give it to me as in a formula. That is correct. Yes, velocity of a volume. Yeah, yeah.
In fluid mechanics, it was area times velocity of the fluid.
Area
Times velocity in fluid mechanics.
Isn't that flow rate? That's flow rate.
Yes.
Yeah.
Oh, and then you times by density.
Beautiful. That's what I'm looking for. Yes, yes. So it's rho times your volumetric flow rate, right? Or we can have it as rho v. It depends on how you want to actually have it. Right. And if we divide by rho on both sides, so what we get is that and that cancels. We're going to end up with 1 over rho. So this is going to be volumetric flow rate. And this is 1 over rho. And 1 over rho, if you remember, is called the specific volume. And mass flow rate will then be your volumetric flow rate divided by a specific volume. Okay. So what we're going to need to get is we have a volumetric flow rate in the system, and that is what you measure with the flow meter. And now we can actually find our mass flow rate. Okay. So what we're going to do, we're going to take it at the actual point 1, which is at the superheat point. Don't worry about that special 0.5 I've put there. I think we'll get to that eventually. And I think the reason why we're going to do that special 0.5, we're gonna have, once we work out our removal of our evaporator, that's we're going to need 0.5. And furthermore, there's something called a pressure drop between the evaporator and compressor. So we're going to see how we can actually play around with get those values. So the first thing you need to do is look at point 1, and we need to get P1 is equal to 100 kilopascals at minus 20. And this, of course, is an actual cycle. We know it's actual because it's superheat on entry. The superheat on entry. So let's quickly get our, what we're going to need there is H1. That's what we always typically get. S1. The reason why we must get S1 because we need to we need to find our H2S, so we can find our temperature. Remember, we have something missing there, and we need to find our V1. So you're going to start to see the problem getting a bit, the few problems with a bit more tricks. Not tricks, but you have to be aware of them. Okay, so I'll give you 2 minutes to get those. Okay, fantastic. 235. Let's have a look at that. Yep. Okay, so let's just get that down. So it's 239.52 S1. Sorry about that. That was 0.9721. Oh man. And of course our, what is this called again? Our specific value is 0.19841 meters cubed per kilogram. Okay, so for us to find our mass flow rate, as I mentioned, so again, obviously finding a property to be a mark. So remember a volumetric flow rate, which important guys is meter, it's 0.5 meters cubed per minute. So we take 0.5 divided by 60 divided by the 0.19841. Okay, and then we can find our mass flow rate. Mr. Minus says 0.042, taking his word that is correct. 0.042. Yeah, it looks within the range. Yeah, your mass flow rates typically for these kind of systems, these are industrial type refrigeration systems. They range within that. Okay, so that's again 2 marks. So I'm making you aware that's your mass flow rate here, right? Shouldn't be difficult to get. Let's quickly see now. So now, remember, we have to find our point 2. So what you're looking for, H2 actual is going to be H1 plus H2S minus H1 over isentropic efficiency. So obviously, if we can find our H2S, we can find our H2A because we have all the other ones here. So we know that S1 equals S2, and so we have to go to our table at 0.8. I think we've done this. Can you just check in the previous table? We had the same pressure. We can actually find our H2S. I think we've done this already. So go to table. Obviously, you've done this. So it should be easy. We found it before, I think, at that particular pressure. Yeah, it's 28481 and 296 at least, yeah. Yeah, this man's gonna kill this section. And you should get 284 point, what's his value? It's H2A is, what's it now? 296. Have a look. 296.67. 296.67. Okay. Kilojoules per kilogram. Cool. Obviously, again, same old. We have to look at our point 3, and we have that at 26 degrees, right? So H3, so T3 is at 26 degrees again. We know it's mostly a function of temperature, not pressure. And H3, which will also be approximately equal to H4, and we can get that value. And be cognizant, I can always ask you what is the quality of the refrigerant, what is the mass flow, Those are the things expected of you. And you'll see the new addition now. Okay, so my H3, H4, you should have gotten 87.83. I think we got this before. Okay, so once we have this, we can work out two things. Let's work out the power input to the compressor and the heat removal. Okay, so you can say WC is m dot times H2A minus H1, 0.042. H2A is going to be 296.67 minus H1, and H1 is going to be 2395.52. And obviously you can also calculate your QL, which is also m dot H1 minus H4. Easy, guys. Easy, 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 easy. What did you guys get? Okay, let's see. 1.872, is that our that doesn't look right to me. We're not actually done yet. So yeah, what is my compressor work? Because our evaporator work we have to still work on. 2.4003, that's correct, yeah. Okay, so now let's unpack our evaporator work. So I deliberately just left that there. So remember, I talked about a new 0.5 over here, right? And for us to find our QL, that is actually going to be, it's going to be H5 minus H4. And they said that and leaves the evaporator at saturated vapor at minus 26 degrees. So we need to go look at for T5 minus 26 degrees. We need to go find H5 now at our saturation our saturation tables there. So if you go to the table, I'll give you a moment to check. I'm checking this myself here. Minus 26, you would get an enthalpy value of 234.70. So be aware of that, those tricks there. 234.70. And once you have that, you can compute your QL. But remember, this is the heat gaining within the evaporator. So that's going to be 0.042234.70 minus H4. So that's a very good question. It's 87.883. That's QL, and we can get QL. Once we're done with that, obviously you can find the COP, which I won't do, but I want to look at the pressure drops within the system. So let's see if we can do that. Okay, so let's just get the QL. Just compute that for me. So we work that out. You should have gotten 6.17, I think. Kilos.
6.173.
Beautiful. Right? Yeah, guys, there's a few marks here you can already see. You should be able to see this. 1, 2. Another mark here. So yeah, this is roughly as hard as it gets. It's just all the other add-on questions which you should know. So can I just get a few thumbs up before I proceed to this next section of work? Yeah. Yes, Nicolene. Go for it.
So, what did you get for power in? Is it power in? Power
Yeah,
input.
your power in should have been 2,4 something. Do you not get these values? So remember we're using H2A minus H1. Must I check?
Okay, thank you.
What did you do?
I'm not sure what I did wrong, but
Oh man, tell us. Yeah,
I
just be
used.
aware. Yes.
I didn't use H2S. I think I used H2.
Yeah, that's why I must be aware. So remember when you're dealing with your yeah. But thanks. It's always good to get some questions. So guys, the other question is now, yeah, great. The pressure drop and the heat gain. Yeah, I'm more looking at the pressure drops between the evaporator and compressor, which is essentially between 5 and 1. But I just want us to write out all our pressures first. At point 1, our pressure was 100 kilopascals. At point 2, we know that it's 800 kilopascals. At point 3, we have 0.75, which is 750 kilopascals. At point 4, what is point 4? Do we know point 4? I have an idea what point 4 is. I don't want to say anything. Oh, point 4 is, I'm not sure. Talk about, and we need point 5. Right? So how do you think we are able to get the pressures at point 4 and at point 5? Who can tell me? Into the starting valve 26 degrees minus 20. Yeah. Mr. Kiefer, do you have any ideas?
Yes, sir. From the table.
Yes, who's it? Yes. So tell me. So how do we get 0.4 and 0.5?
For 0.5, not sure about 0.4. 0.5, we
Yeah.
go from the minus 26. The
Beautiful.
pressure is at 0.5.
Yes, there we go. That is what I'm looking for. So what I'm making you aware of, there might be questions where I ask you find pressure drops within the system, right? Like I said, this is for the men and the women, the seconds and the chiefs, not the ELWs. And what you basically do is have a look at minus 26, and you can see there's a pressure of 101.73, right? So we know that this pressure is 101.73. This pressure is the same by the virtue that it's a constant pressure heat removal, and obviously it lies on the same line as this over there. So there's no pressure drop assumed to be which occurs between the two within the evaporator itself. However, there is a pressure drop occurring from 0.5 to 1, which is entry to the compressor, entry to the evaporator, the compressor, and after final pressure drop, which the one is going to be 0.5. That's going to be P5 minus P1, which is 101. Was it 23 again? What did I have there? 101.73, sorry, minus 100. And you should get obviously 0.73 kilopascals. You guys get that? So that's how you find it. You find this pressure at minus 26.
So the value is 1,73.
1,73. No minutes.
The pressure drop.
Oh,
It's
1,73. Oh, yes. Sorry, man. My apologies. Yeah, I agree. Nothing critical there. So that is how you're going to find the pressures through the system. So see, this is a very complex question. Very procedural. One just needs to know certain things. So what I also recommend. Okay, so we basically end off refrigeration now. Maybe that's a good thing for you guys, but it's quite sad for me. I'd love to stay on this section. Have a look at the problems at the back. At the back of the chapter, there's some good questions you should actually look at. Just looking now. So remember, we don't do any second law, so I'm just making you aware of the stuff. Let me just look at this one. This is under second law, and I'll paste it for you now here. Okay, you guys probably won't see it like that here, so I'll just get it here. So is there any questions before I actually close this section off? So I hope you learned something there. Okay, I'll give you something to do. Maybe you'll touch on it. Maybe next week I'll ask you guys if you've done it. This actually, I don't know why this says bullets here. I'm removing this other text here. So guys, are there any questions before we move on? Yeah, there's one question I want to show you guys. Okay. Let's just show you. Is that someone's hand? Okay, no, nothing. Okay, guys, here's a nice question, and it says bananas are to be cooled from 28 degrees to 12 degrees at a rate of 114 kilograms per hour by a refrigerator that operates on a vapor compression cycle. The power input is 8.6. Determine the rate of heat absorbed by the bananas in kilojoules per hour. The COP and the minimum. So this is a question actual within the textbook under the second law side, but obviously we can find this, and obviously we can assume that the assumption that the cycle is an ideal cycle. So I'm just showing you, like a question which is, I can ask a question like that maybe, where it looks particularly difficult, but it's really not. So I don't know if you guys are able to interpret that question. I'm just letting you know, like, what kind of stuff one can possibly get with this kind of stuff. It's not difficult at all, but it looks tricky. I did want to touch on heat pump systems, but obviously this is not a, you guys are not, it's not a technology you guys are aware of. Yeah, so that's a bit of an interesting one. You can actually try and play around with, and see if you're able to solve it. It's not that difficult. I wonder but the idea is that this here is your QL, right? You need to find basically QC, and obviously you have to find the power. And so I don't know what, and obviously we have WC, and if the bananas are cooled from 28 to 12, yeah, I wonder if this is possible. If you guys can solve something like this. And also the other thing that I want to actually do, and this is what I want to show you, was looking at the effects of evaporating pressure and temperature on a simple system. And what would be nice if you can just take this particular example and you investigate, keeping all other parameters constant, the investigate the effects of evaporation temperature, and the effects of or increasing the condenser temperature, right? And these are the kind of stuff one really wants to look at for like prop analysis, to see that, okay, so especially when you have a system, an actual system, you can actually understand how things behave properly. So this is another homework exercise I wanted to give you guys, and the answers are, I actually want to maybe, I'll give it to you guys when I see you guys next time. What happens if you increase evaporation temperature? What happens to the cooling load? What happens to the compressor work? What happens to the COP? If you increase the condensing pressures from 5, 6, 7, 8, in fact, maybe we can just say from 800, 900 to 1,000 maybe, which is really it's really a big jump. And look what happens to the QL, WC and COP. Write a small paragraph and probably some reasonings. So this is the kind of stuff I actually want to touch on to make this, this thing more in depth versus solving all other problems. But check the problems at the end of what is this? At the end of single, and yeah, I was going to introduce a few other things, but like I said, it's just in the interest of time. I'm going to just say end of lectures. Because normally, typically do all the advanced stuff. Like when I did all my advanced cycles, we normally do that in BTEC. Like we have your cascades and all of that, and you look at your cooling loads, and we can cut in depth in terms of, not difficult obviously, just in depth in terms of how you work out typical cooling load, which kind of talks to this kind of thing. Yeah, maybe, yeah, anyway, that's all guys for vapor compression for refrigeration cycle. So is there any questions maybe on your end? Because we basically reached the end. Can I have a small engagement maybe? No questions, guys. It's Friday.
Seems like a nice section, sir.
Yeah, no, it is. Even the next section you're probably gonna enjoy. Yeah. Heat transfer, that's gonna be fun. It's not difficult, guys. I mean, I don't know how people fail, honestly. Like I said, the sections can become out of hand. Thanks for responding, Mr. Doyle. But it's all within it's all delineated for you, so you know exactly what you kind of expect. Just gotta practice a few of these problems, and then yeah. In essence, it's procedural. Anyway, the last thing I just want to show you, yeah, I'll load the slides today, but those questions are all within your textbook, so you don't have to really worry. But like I said, if I had like 4 weeks, 5 weeks, could have done advanced cycles where what I'm looking at, we have basically what we do over here is called cascading a system, and we have 2 compressors essentially. And what we can do with this kind of system, we can actually further increase the temperatures. Like remember I talked about getting it, like medium. We typically deal with medium application, but when you go with more high temperature, you can actually cool further with 2 compressors. We can actually take it cooler. We can have a 2 evaporator system, which is basically what you have in your house in essence, with your freezer and your freezer kind of setup. You can look at that. It's not particularly difficult, but yeah, in the interest of time, the depth is kind of, we don't have a lot of depth. Yeah, there's a few other things, and the gas refrigeration cycle, which I'll talk about. And within the gas refrigeration cycle, basically is the Brayton cycle. And we basically, instead of going the one way, like the typical heat engine, we go the other way. I initially introduced this, when I started thermos. But yeah, I will, maybe when I have more time next year, and maybe I shouldn't focus too much on, yeah, just anyway. So yeah, guys, that's the end of that section. We can have a break. What time is it now? 10 minutes. You can start at 10 past 12, and then you can start on our heat transfer. Yeah, we're gonna cover a lot, and then next week you'll do a bit more heat transfer, and then start on air compressors. Yeah, so I've made things fairly easy for thermos. You just have to go over the lectures and practice. Okay, guys, see you at 10 past 12 for our next session on heat transfer. So there's another heat transfer link, so just please join that one. So thank you.